Hello and welcome to the third of the lectures in this week under the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the previous two lectures, we had looked at coming up with an axiomatic definition of one particular generalization of conjunctions to the setting of fuzzy sets, that of T-norms in brief, triangular norms. We've also seen some analytical aspects of triangular norms, especially different types of continuity. In this lecture, we will look at some algebraic aspects of T-norms, both at the elemental level and also at the level of functions. And with that, we will give some simple classifications of T-norms themselves. And what is interesting is, we will also see that based on the order theoretic and analytic and algebraic properties that they enjoy, the confluence of these three sets of properties actually will give rise to some interesting characterization of T-norms on the unit interval 0. Let's look at some algebraic properties at the level of an element. So to begin with, we fix a T-norm T and take an element A from the unit interval 0. Let's introduce some notation. So A is an arbitrary element, T is a fixed T-norm, and what do we understand by this symbol? So if n is 1, then this is simply A. If n is 2, then this is simply P of A. And for all n greater than or equal to 3, we can write this as T of A, AT of n minus 1. So recursively we define this. It is clear that if n is equal to 3, then AT of 3 is T of A, AT of n minus 1, 2, which can be written as T of A, T of A, A. Now, by associativity, we can remove this and talk about this itself. So by associativity, this binary operation can be extended to n-ary operation. So if you look at this, we could just think of it as operating A on itself n times. Once again, the associativity of T allows us to look at this particular operation like this. Now, given an element A, when do we say it is idempotent? This is familiar to us. This with respect to the T, if T of A is equal to A. So, we are going to talk about properties of an element with respect to fixed T. So, idempotence is very well known to us. What is nilpotent? When do we say an element is nilpotent? If there exists an n, a natural number n, such that AT of n is 0. What does that mean? It means that if an element were to be nilpotent, if you operate on it countably finite number of times, it should become 0. Where I'm using the infix notation, the star is a T-norm T. So if an element possesses this property with respect to the chosen T-norm, we say that element is a nilpotent element with respect to the T-norm T. When do we say an element is a zero-divisor? This concept should be familiar to you again. If there exists a B in the open interval 0, 1 such that T of AB is 0. Now, this is much like you take an A, element of 0, 1, and find a B in open 0, open 1, such that T of AB is 0. Perhaps you recognize this if you were to write it as neat. A and B is 0. This is what we have seen as the complement of an element in the setting of lattices. Here we are looking at it as a zero-divisor. Note that when A is 0, then for any B practically, in the open interval, T of AB is 0 for any T. And if A is equal to 1, then b cannot come from an open interval 0, 1 because t of 1 comma b is actually b, and this will be 0 if and only if b is equal to 0. So essentially, when we talk about nilpotents and zero-divisors, we will consider the A to come from open interval 0, 1. Okay, let's look at these three algebraic properties that we can define with respect to an element and a given fixed t. How do our familiar t-norms behave, or what are the corresponding sets of idempotent, nilpotent and zero-divisors with respect to these 5 t-norms? Let's look at that. We know that, so we are looking at idempotence. That means let us indicate by it set of all A in 0, 1 such that t of A is equal to A. Now, if t is the minimum t-norm, Tn, then we know that this is the entire interval 0, 1, because we have seen that minimum is the only idempotent t-norm. In fact, if you consider 0, A to be 0 or A to be 1, then for any t-norm, these are idempotent elements. In fact, they are called the trivial idempotent elements. And we also know that for the product t-norm, Tp, we do not have any idempotent elements, because if you take this to be Tp, then t of A is A square. If you want this to be A, then this can happen only if A is 0 or A is equal to 1. So it has only the trivial idempotent elements. We have seen that the Lukasiewicz conjunction is not idempotent. The drastic t-norm, almost everywhere it is 0, it is not idempotent. But what about the nilpotent minimum itself? Does it have any idempotent elements? Well, let's look at the definition of nilpotent minimum. We'll preserve this for a moment. It says it is 0 if x plus y is less than or equal to 1 and minimum of x comma y if x plus y is greater than 1. Now we see that you have the minimum operation coming into picture here. If you take 0.6 as A, look at t of 0.6 comma 0.6 with respect to minimum to minimum. 0.6 plus 0.6 is greater than 1, so it is minimum of these two, which means it is 0.6. That means nilpotent minimum does have idempotent elements, non-trivial idempotent elements. But what exactly are they? How do we find them out? Let's look at their graphs. So on the left you have the minimum t-norm, on the right you have the nilpotent minimum t-norm. And it is easy to see immediately that we have obtained this nilpotent minimum from the minimum by reducing some part of the graph to the 0 region. Right. Now, consider the diagonal of the unit cube, not diagonal of the square, diagonal of the unit cube. We know that if it has to be idempotent, that element, the value that it should take at that point on the diagonal, t of A should be actually 1. That means the graph of the corresponding t-norm should be touching this line. You see that for the minimum, it touches everywhere. For the nilpotent minimum, it touches only from open 0.5 to 1. Whereas on this line, it is 0. So if you see from this point of view, everybody here is actually idempotent. So it's easy to see, it can also be worked out from the formula, that if you look at it, the minimum t-norm, the idempotent set is the entire 0, 1 interval, whereas for the product, Lukasiewicz and drastic, they have only the trivial idempotent elements. And in the case of nilpotent minimum, of course, other than the trivial idempotent elements, the entire open interval 0.5, 1, every element in this interval is an idempotent element. Now, let's look at what is nilpotence and how to find the nilpotent set for a given t-norm t. So, what is nilpotence? You fix a t, you take an x element of 0, 1, open 0, 1. Note that once again here, that if x is 0, then it does not go anywhere. So, what we want here is that there should exist an n such that x t of n, which is nothing but x composed with itself n times, should become 0, where by the infix notation, I am denoting the t-norm t. So this is what should happen. If x is 0, then clearly 0 star 0 is 0. And if x is 1, we know that how many ever times you operate 1 with itself, it is not going to go to 0. So typically when we talk about nilpotent elements and zero-divisors, we exclude the endpoints, both 0 and 1. So now let x come from the open interval 0. Now if you look at t to be tn, take any x, any a in 0, 1, open 0, 1. And what we see is t of a is a, t of a is again by associativity a. Because every element is idempotent element, it cannot be a nilpotent element. For the minimum, we do not have any nilpotent elements. What about the product? Well, if you take Tp, then x Tp of n means x dot x dot x n times is nothing but x power n. Now remember, x comes from the open interval 0, 1. Now we know that the limiting case n tends to infinity, x power n is 0. However, for no finite or countably finite n, it is going to touch 0, which means no element is a nilpotent element here. What about the Lukasiewicz t-norm? Yes, it can be seen that if we consider this, let's take x to be 0.7. Now, 0.7 with respect to Lukasiewicz, let's do 2, n is equal to 2. That means it is t of 0.7, 0.7. By definition, we know this maximum of 0, x plus y minus 1. So this will turn out to be 0.4. Now, if you iterate once more, 0.7 with respect to t of 3 and 3, what we get is t of 0.7, t of 0.7, 0.7, which is nothing but t of 0.7, 0.4. Now, this is max of 0 or 0.7 plus 0.4 minus 1. This is 0.1. Now you see that it is already decreasing. Take 4, then it is t of 0.7, xt 0.7 t of k of 3, which we know is 1, 0.1 is 0.1 with respect to 8. Now you see here, maximum of 0, 0.7 plus 0.1 minus 1, this is 0. So if you take 0.7, in practically 4 steps, it is 0. That means for n is equal to 4, 0.7 being operated on itself with the Lukasiewicz t-norm goes to 0. So this is a nilpotent element of the Lukasiewicz t-norm. If you work out like this, we will see that the entire open interval 0, 1 are nilpotent elements for Lukasiewicz and also for the drastic t-norm. However, for the nilpotent minimum t-norm, what we have is only the values belonging to 0 to close to 0.5, they become nilpotent elements. This can be easily worked out. Now, let's look at zero-divisor. So what does zero-divisor say? If you have an element A, once again, we are only considering the open interval 0, 1. As was already mentioned, we will interchangeably use either this notation or this notation to indicate the open interval, openness of the intervals on either side. Then we need a B, once again in open interval 0, 1, such that T of AB should be equal to 0. Now, instead of working out on the sheet, let's try to see whether we can look at it from a geometric perspective. Now, these are the 3 t-norms that we have. On the top left is the Lukasiewicz, top right is the nilpotent minimum, and on the bottom is the drastic minimum. Now you will see here, definitely all of them have zero-divisors, because you have essentially for zero-divisor, what do we need? 2 elements A and B, neither of which is 0, but T of AB is 0. You see here, everybody in this region almost satisfy any pair you take here, a comma b, t of ab is 0. Similar is the case here, and similar is the case here. That means they have zero divisors. On the other hand, if you consider minimum and product, you see that they are actually becoming 0 only at the boundaries when either x is 0 or y is 0, as mandated by the T-norm because of its monotonicity. Nowhere else they become 0. That means these are two T-norms that do not have zero divisors, whereas these three T-norms, among the 5 that we are considering, they all have zero divisors. If you work out, it will be interesting to see that minimum and product, as we have seen, the zero divisor set is empty. However, every element in the open interval 0, 1 is a zero divisor for all the three T-norms: Lukasiewicz, drastic, and nilpotent minimum. Now, some interesting observations can be made. If you look at the intersection between the set of all idempotent elements, which you have denoted by IT, and set of all nilpotent elements, which we are denoting by NT, what about this intersection? Clearly, it is empty, because if an element is idempotent, it cannot be nilpotent. If it is idempotent, how many times you iterate with itself, it is not going to move an edge. It stays there. It cannot go to 0. So, an idempotent element is never an nilpotent element. However, if you consider the intersection with the set of zero divisors of the T, then we see that it can be non-empty. For example, you see here, this is for the nilpotent minimum, we see that 0.6 is in fact an idempotent element. However, 0.6 is also a zero divisor. This can be seen like this. So consider, so we have the definition of nilpotent minimum here. So now 0.6 we have taken, we know it is an idempotent element, but it also can act as a zero divisor. For whom? Say for 0.3. Look at what is T of 0.6, 0.3. This is 0.6 plus 0.3 is less than or equal to 1, so it is 0. So that means 0.3 is a zero divisor for 0.6, and so is 0.6 a zero divisor for 0.3. So an idempotent element can also be a zero divisor. Now, what about these two sets? The set of all nilpotent elements of T and the zero divisors. It can be easily seen that every nilpotent element is also a zero divisor. Now, how do we see this? So if an A belongs to NT, that means there exists an element of N such that A T power N is equal to 0. Now, what is this A T power? You can write it as T of A comma A T power N minus 1. Now, call this B. So then what you have is T of A comma B is 0. So for this A, there exists another B such that it is equal to 0. So B becomes a zero divisor for A, and so does A becomes a zero divisor for B. So every nilpotent element is also a zero divisor. Now, if you look at the final equivalent, so if NT is not empty, the set of all nilpotent elements is not empty, clearly ZT also cannot be empty. However, the reverse, the converse implication, that is what is interesting. So if the set of zero divisors is not empty, then it also shows that the set of nilpotent elements is non-empty. How do we show this? Once again, let's look at this. So now let A belong to ZT. This means there exists a B element of open 0, 1 such that T of AB is equal to 0. Now note that both A and B, they come from the 0, 1 interval, open 0, 1 interval. That means either A is less than B or B is less than A. Let's assume for a moment that B is less than A. Now what we know is then, if we consider T of AB, this is in fact by monotonicity is greater than T of BB. But this itself is 0. So which means T of BB is 0. But what is T of BB? BT of 2 is 0. So there exists an N, in this case actually it is 2, such that BT of 2 is 0, which means B becomes an nilpotent element. So however, note that not every zero divisor is also a nilpotent element. For example, in the case of nilpotent minimum, we saw that 0.6 is a zero divisor. It belongs to ZT, but 0.6 also belongs to IT, idempotent element, And since it's an idempotent element, it cannot be an important element. Well, we have introduced these three concepts of idempotence, nilpotence, and zero-divisor. How do these help us? Let's look at this. If an element is an idempotent element of a T0, what do we know? We know that for every x greater than or equal to a, then T of Ax is a. Now, once again, this can be easily proven by monotonicity. What do we have? We have a element of IP. And what we need to prove is T of Ax is equal to a for all x in a. So now take any x. X is greater than or equal to a. So that means this is greater than T of a. But we know by monotonicity this is smaller than T of a1. This is a because 1 is the identity, and this is a because it is idempotent element. That means T of Ax is a. Now, other than the algebraic manipulation that we have done and shown this, what does it mean geometrically? Look at this. This is the skeletal framework of a T. The dotted line in magenta is actually the diagonal of the cube. We know that if a point is idempotent, then it actually falls on this diagonal of the cube. So let's assume that point 4 is one such a point. It's idempotent for a particular T that we're considering. What it means is at T of 0.4, it is 0.4. Now T of 1, 0.4 is also 0.4. And what we see that is because of monotonicity, it has to be a constant here. Now this allows us to imagine the graph of a T0 at the point which is an idempotent element. So it allows you to visualize a T0 quite effectively. And if you want to sketch the graph of a particular T0, making use of these things, making use of the elements which are either idempotent or zero-divisor, you will have a good idea of how the graph would look like. Often this is very important when you are choosing T-norms in a particular context. Well, so far we have seen algebraic properties of an element with respect to a T-norm. Now let's look at some of the algebraic properties that T-norms themselves enjoy, or how to classify them based on the algebraic properties they enjoy. Given a T-norm, we say it is strictly monotone if you have an x which is greater than 0 and y less than z, then we should have that T of xy is less than T of xz. Essentially, it says that it should be strictly increasing other than on the boundary. And x is 0, anyway it is a constant 0. Everywhere else it should be strictly increasing. We can also talk about Argumentativeness. What it says is, take any pair of elements xy in the open unit square, 0, 1 square. There should exist an n such that after operating x with itself n number of times, the value should become smaller than y. We look at it presently. Once again, we want to discuss this in the light of the 5 T-norms that we are considering. But what we would like you to notice specifically is the role of the underlying order. For Archimedeanness and strict monotonicity, we see that the order that is available on the 0-1 interval is actually playing a role. Archimedeanness, we take the element and operate with respect to the T-norm iteratively. In the case of strict monotonicity, we are claiming that it should be compatible with the underlying order, that is monotonicity, but we also want it to be strictly monotonic. Now, let's consider these 5 T-norms in terms of strict monotonicity. Once again, we will go for some visual cue to help us in identifying whether these T-norms are strictly monotonic or not. Look at these 3 T-norms: the Okasiewicz, nilpotent minimum, and the drastic minimum. Strict monotonicity, we understand, means the graph cannot be constant anywhere other than on the 0 boundary. That is where x is 0 or y is 0. And you see here, while in this region it is strict, we see that there is a constant region here. Similarly here and similarly here. So that means these 3 T-norms are not strictly monotonic. What about minimum on product? Well, they are 0 only on the boundary, but if you look at minimum, because every element is idempotent, from that point onwards, it actually becomes a constant. So it increases, say 0.4 is an idempotent element, it increases till 0.4, but as we have seen a few slides earlier, from 0.4 to 1, t of 0.4 comma x, when x comes from 0.4 to 1, is actually a constant at 0.4. So this is also not strictly monotone. However, we know product, we take two elements which are distinct or same, we always get some values different from both the operands, unless one of them is 0 or x is equal to 1. So among the 5 t-norms, what we see is only the product t-norm is actually strictly monotone. What about the Archimedean property? How do we understand this? So now we are given two elements x and y in the open interval 0, 1. What we want to do is, if we want to say that the t-norm enjoys Archimedean property for any arbitrary pair x, y, we should be able to find an n such that x, when operated with itself n times, should become smaller than 1. Now, let's look at the different t-norms that we have. In the case of minimum, we see that this is not going to be possible because any a you take, a t of n will actually be a. So if you take your y to be smaller than a, then this is not going to happen. So the minimum t-norm does not satisfy or enjoy the Archimedean property. What about the product t-norm? Now if we take an x, an open interval, then we know that xt of n with respect to product is nothing but x power n. We see that in the limiting case, as n tends to infinity, it does go to 0. So now, no matter which y you give, you will be able to find some n such that x power n is smaller than 1. So this is basically coming from convergence of this sequence. Now, let's see whether we can take some visual cue for this. These are the minimum and nilpotent minimum t-norms. You see that they have an idempotent element. The moment they have an idempotent element, immediately we see that it cannot enjoy the Archimedean property because iterating the idempotent element with itself does not lead you to some other value. So these two t-norms are do not enjoy the Archimedean property. However, we can show in the case of drastic t-norm, any 2 points you take, p of x y is 0. So clearly, you see that given x, you are going to fall to 0. So is the case with product. And we have seen that every element in the Lukasiewicz, for the Lukasiewicz t-norm, is a nilpotent element. That means after finitely many, or countably finite many, for a particular n that we can choose fixed, so in that sense, we could say it is also finite, xt power n actually is 0, which means again, for any y that you give, we can find an n such that xt power n is less than 1. So based on this, we say that among these 5 t-norms, other than minimum and nilpotent minimum, other 3 do enjoy the Archimedean property. Now, this is perhaps the first time that we are seeing more blue than red. Let's also add continuity into this framework. And you see that the first 3 are continuous t-norms, the last 2 are not. We have seen that many times before. Now, it's interesting to note that if it is both strict and Archimedean, we seem to see that it is also continuous. But is it really true? Can we generalize this from just one example? Let's look at another example. This is essentially product t-norm half by half. So this is how the graph looks like. It is clear now that this is strictly monotone, nowhere it is constant. However, it is not continuous. And also we see that it will enjoy the Archimedean property because it essentially goes to 0. For instance, if you iterate for this t-norm, take an x and iterate it, xt power n will be essentially x n plus 1 by 2 power n. It keeps on happening. So clearly this goes to 0 as n tends to infinity, which means that given any y, we will always be able to find an n so that xt power n is smaller than 1. So this is a t-norm which is both strictly monotone and satisfies the Archimedean property, but it is not continuous. Once again, you will see that it does not have any non-trivial idempotent elements, And once again, there are no nilpotent elements and there are no zero-divisors. So if you look at, introduce this t-norm also into this table, this is how it will look like. Well, why these two concepts of strictly monotone and Argumentativeness? It will become clear soon enough when we look into the applications also soon. But for now, let's look at two particular classes of t-norms. We call a t-norm to be strict if it is both strictly monotone and continuous. We understand when a t-norm is continuous, the usual definition of continuity applies here. And we say a t-norm is nilpotent if it is both continuous and the set of nilpotent elements is the entire 0-1 interval. That means every element is nilpotent. And among the t-norms that we have seen, we saw that the product t-norm is both continuous and strictly monotone. Similarly, the nilpotent t-norm, an example of that is the Lukasiewicz t-norm, which is both continuous and every element is a nilpotent element. In fact, what is interesting is these are essentially the prototypical examples for this class or these classes of t-norms. That means it can be shown that every strict t-norm is somehow related to product and every nilpotent t-norm is related to the Lukasiewicz t-norm. We will see this perhaps in one of the next following lectures. Now, so far what we have seen is algebraic properties of elements and properties at the function level itself, algebraic properties at the function level itself. Now let's do something more. Let's take t, which is a binary operation of 0, 1, and look at it from order, algebraic, and analytic perspectives. Because it has continuity, it has some order underneath, and it has some nice algebraic properties also. Now, if you look at the kind of structure that you can have on set X, you could have an algebraic structure like groups, vector spaces. You could have an order theoretic structure. We have seen cosets, lattices, chains, different special types of lattices. And on the same set X, you could also have some analytical structures like that of metric spaces or topological spaces. Now, what we see here is for a t-norm, if you look at it in terms of the properties that you can enjoy, there are some algebraic properties like commutativity, associativity, and identity. There are order properties, which is essentially making use of the underlying order on 0, 1. The monotonicity comes from there. And it also can be made continuous. So you can also consider continuous t-norm. So now let's look at how these three properties come together and show what a t-norm can do to the unit interval. What kind of structures it can impose on the unit interval 0, 1. Given a set X and a binary operation which is closed on it, that means star is from X cross X to X. If it is also associated, we call it a semigroup. If it also has an identity, we call it a monad. And what we know is if we take the set 0, 1 and t, consider t-norm as just a binary operation, we see that based on its properties, it is actually a commutative monad, associative, commutative, and an identity element basis. Now note that if you have a set with a binary operation, closed binary operation on it, and a special element 1, and also an ordering on the underlying set, such that this x star 1 is a monoid, and with respect to this ordering, either it's a coset or a chain, what have you. Now we can define what is an ordered monad. It is nothing but the operation, the binary operation star, respects the underlying order. It is compatible with the existing order on the set X. So A less than or equal to B implies A star C is less than or equal to B star C. We know that immediately T satisfies this with respect to the usual order on 0. What is an integral monad? Since it's a monad, it has an identity, both left and right. If this identity is also the top element, then we call it an integral monad. That is, the identity should be the maximum element. Every other element should be smaller than that with respect to the order that you have on the set X. Now clearly you see that if you consider 0, 1 with the usual order on it and any t-norm, it is a commutative, totally ordered, plus 0, 1 with respect to the usual order is totally ordered. This structure is a commutative, totally ordered, integral monoid. Now, let's throw in some analytical properties. Consider a closed subinterval of R, finite, and consider an operation on that which makes it a semigroup. Also, since on R we have the usual metric and topology, let the star be continuous with respect to that topology or metric. Further, in this structure, let the endpoints be such that one of the endpoints is an annihilator and the other is an identity. So either A is an annihilator and B is an identity, or B is an annihilator and A is an identity of star. What do we understand by an annihilator? So annihilator means if you have A, we say A is an annihilator if A star x is equal to A for all x coming from that set x. By identity, we understand B is an identity if B star x is actually equal to x. So now, what do we know here? If you consider a continuous T on the 0-1 interval, we consider T as a binary operation, a continuous T, we immediately know or see it is an I semigroup. Now comes in the familiar Lukasiewicz conjunction. So since Lukasiewicz conjunction is continuous, what we see is on 0-1, it forms an I semigroup. You may remember that the Lukasiewicz conjunction in its dual disjunction, the pair came very close to giving us a lattice, but now they are happily giving us an I semigroup. It's not only that. If you put all these properties together, what we get is this very interesting result. If you consider 0-1 with the usual order and the continuous T, it becomes a totally ordered integral commutative I semigroup. There's a nice, very rich algebraic structure that you could have on the unit interval through a continuous T. A quick recap of what we have seen today. We have looked at algebraic properties at the elemental level and also at the function level, which allowed us to talk about at least two types of T-norms, strictly monotone and those which are Archimedean. We have seen how the confluence of order theoretic, algebraic and analytic properties has given a nice characterization of T-norms on the set on the unit interval. Now, what next? Using some of these results, we have come up with many constructions of T-norms. We will look at a few of them in the next lecture. They would definitely be useful for us when we deal with application of context. So that would form the topic of our next lecture for this week, different types of constructions of T-norms. A good resource that you could look up to for the topics that are covered in this lecture is the book by Clement, Messier and Parr. So thank you once again for joining me in this lecture and hope to see you again in the next lecture. Thank you.